All right. Hello, everyone. Welcome back to our weekly physics review. This is for Intro Physics 1. And today we are going to be talking about projectile motion. So last time we started the entire course with kinematics, 1D kinematics, and we reviewed position as a function of time, velocity as a function of time, acceleration as well, although we said acceleration is going to be constant for the most part. And we studied motion, but in one direction. So either along the x direction, maybe the horizontal, or the vertical. We did some free fall, things of that nature. And, we only focus on kinematics in one dimension because before we move on to projectile motion, we kind of needed to get comfortable with those equations. Now, the goal of today is to cover a specific topic, which is projectile motion, of course. And really, it's just more of the same. So it's going to be a good review for what we've already talked about, and it's going to hopefully solidify kinematics in your mind, because the nice thing about projectile motion, which is why it's typically something that we teach in intro physics, is that you get motion simultaneously along x and along y. However, along x there is no acceleration, whereas along y there is a constant acceleration. And so you get both types of motion, motion at constant velocity, and then motion at constant acceleration, constant non-zero acceleration. And therefore, you can use the kinematic equations that we talked about last time, and you can just have both types of motion at the same time, if you will, just along different directions. So it's a very common topic to teach. It's a very, how do I say? I mean, it's a very interesting topic in the sense that it does attempt to explain, or at least describe, the motion, let's say, of anything you would launch through the atmosphere. So if you hit a golf ball, or you launch a cannonball, or maybe you turn on a drinking fountain and you see the parabolic path followed by the water as it flows out, that's all projectile motion. Now, of course, it's an idealization because we neglect air resistance and anything but weight, but if you can accept the idealization, at least it's a good first model to describe the type of behavior while things fly through the atmosphere. So we are going to dive into it today. We're going to start with a quick definition and recap of projectile motion kinematic equations, and then setting up a projectile motion problem, and then we'll apply that to a couple of practice problems to illustrate what you might expect in terms of practice problems. As usual, let's just go through the resources real quick. You can find all of these live streams along with the practice problems and solved homework problems at slackademia.com/livestreams. You can sign up for the free Physics 8A live stream course. Everything's packaged in there, so it's nice and easy to find, and everything's organized. And if you want more help, if you want customized help for your specific class, you can either sign up for a study guide if it's already on the website. If it's not, you can send us your syllabus and we will create one. And then once it's on the website, you can sign up. Move pretty quickly. If you send us your syllabus, you can probably get a study guide set up in a day maybe, and then you can go have a look. And then as you sign up for the study guide, you can choose between just study guide or Masterclass. Masterclass gives you more options, so you get access to me all semester or the whole quarter, depending on your course, and there's a grade guarantee. So if you don't get some kind of A minus, A plus, we will refund you 90% of your Masterclass subscription. So something to think about if you need a lot of help and you think that it would be a good thing to have someone in your corner that can help you think through physics and answer your questions as you go. So that's an option. Feel free to check it out. It is a good deal because if you don't get some kind of A, you do get a refund. All right. So with all of that said, now that we're done with the administrivia stuff, let's talk about projectile motion. So I put down the definition just because it's always nice to have a definition. And what we mean when we say projectile motion is basically we're referring to the two-dimensional path that is followed by an object that is acted upon solely by its weight as it moves through the atmosphere. And then the path itself that this object will follow is entirely determined and characterized by the initial velocity, v0, and the launch angle. So, a few things about this definition. Let's start with drawing roughly what this might look like. Okay, so this is a very approximate drawing, but something like this. If you were to launch a golf ball from the ground, let's say, with a certain velocity v0 and a certain launch angle theta, it would then follow this parabolic path through the atmosphere, assuming, of course, that you could say that it is being acted upon solely by its weight. Now, that's kind of what makes this definition not a great definition, at least for now. Now, as soon as next week rolls around, definition is going to make a lot more sense because we will know what the weight force is. But right now we don't know about forces. We don't know what the weight is. So I'm going to have to draw something that will make sense later, but I'll do it now so that you can refer back to it. And that's going to be the weight force. Now the weight force, I mean, in everyday life we kind of understand what that means. It's basically how heavy an object is, right? And so it has a magnitude mg, right? I'm just going to draw it like that. And I'm going to draw it at 3 different locations only to say that there are no other forces acting on the projectile at that point. So your projectile has to be left on its own after it's launched. So if you throw a football, if you hit a golf ball, if you launch a cannonball, once it is launched, there should be nothing else interfering. Now, there will always be air resistance in real life. We just choose to neglect it because it makes things harder, okay? Not that we couldn't deal with air resistance, but it does make things substantially harder. And so again, let's walk before we run. And neglecting that, there can be no other force. That means that there cannot be a parachute that slows it down, right, as it falls. It can't be a firework that is launched by, you know, the thrust of burning propellant and thrusting it forward. That's a thrust force, and we can't have that, right? You can't have something that can be self-propelled or can be slowed down by a parachute or air resistance or anything else. You can just launch a projectile and let it go. As long as there's only weight acting on it, you can then predict the path it's going to follow, how long it's going to spend in the air, where it's going to fall, and so on and so forth. And so this is what we mean when we say projectile motion. So it means something very specific, right? And we're going to need not only the x direction, because yes, we move from left to right, but we're also going to need the y direction, because while we move from left to right, while the projectile goes from left to right, it also moves up and then down. So we have motion along 2 directions here. And what we're saying is that your launch angle, theta, and your initial velocity fully determine the path followed by the object. And as we're going to see, everything we're going to derive, the time of flight, the range, the max height, all of it is only a function of v0 and theta. Okay? So what we need to do is we need to get good at applying the kinematic equations we learned about last week, but along x and along y at the same time. Okay? So how do we do that? Well, let's recall that when it comes to kinematic equations, we are looking for 3 things. All right, now recall that last week we said, okay, x of t, assuming a constant acceleration, is going to look something like this. 1/2 axt squared plus v naught x t plus x naught, and velocity as a function of time is just going to be axt plus v naught x. Right? And these 2 equations go together, right? They're called parametric equations. They're in terms of a parameter t. And if you tell me t, I will tell you where you are on the x-axis and how fast you're moving in the x direction. And I'll even tell you if it's to the left or to the right. Okay? Now, of course, that's just for one direction of space, right? So the same way we wrote this for x we can write it for y. Now it has no reason to look any different. It's be 1/2 ay t squared instead, plus v naught y t plus y naught, and then here it's going to be vy of t is equal to ay t plus v naught y. Okay, but we need both because we have motion in both directions. Okay, now, like I said, we're going to try to find ax v naught x x naught, ay v naught y y naught. If we have that, then we have our kinematic equations, and they will describe the flight of the projectile from the moment it is launched, from the moment to the moment it hits the ground. By the way, just to clarify, obviously to launch, let's say a golf ball, to launch the golf ball you have to hit it, right? Which means that, well, do we worry about the hitting? Like, do we worry about how much force is applied by the golf club onto the golf ball so that we can figure out V0? And the answer is no. So the problem begins in projectile motion the moment the projectile is launched. So the moment it launches with V0, that's when the problem begins. We do not worry about how it is being launched. Okay? Now, I'm not saying we'll never worry about it, but what I'm saying is that the equations that we set up start to be valid once the projectile has been launched. Okay? So we don't worry about how it happened from the point of view of our kinematic equations. All right. Now, let's find acceleration, initial velocity, and initial position along x and y. Let's start with acceleration because it turns out it's the easiest one. Okay? Now, we talked about this last week when we talked about free fall. And then we said that the acceleration in the y direction, so long as I choose y as positive up, is going to be minus g. G is the acceleration due to gravity. It's 9.8 meters per second squared near the surface of the Earth. And it points straight down, and since down is negative, there's a minus. Okay? And in fact, because gravity points straight down, and gravity, again, we don't know this yet, but comes from weight, right? It comes from the weight force. So once we know Newton's second law, this is going to make a lot more sense. But for now, we're just going to say, okay, well, all we have is gravity because actually the only force acting on the object is a weight. And so that means that a sub x, the acceleration in the x direction, is 0. Now, to have an acceleration in the x direction, maybe I would need this to be, again, a firework that is being thrusted, forward like that. Then, okay, I would have an acceleration horizontally. But here I'm not going to have a horizontal acceleration. In other words, the shadow of the golf ball on the lawn moves at constant speed as the ball flies through the air because there is no acceleration. Okay, so that's acceleration. That's helpful. Then we need to figure out the components of velocity, right? Because if we look at it, initial velocity, v0, is not purely along x or purely along y. It's along both. It launches both to the right and upward. So let me make a little bit of room so that we can work out some details here. And we're going to need to find the components of v naught. Okay, so let's say this is v naught. It's going to have two components, right? It's going to have an x component, call it v naught x, and then it's going to have a y component, v naught y. Okay. Now sometimes what we'll do is we'll draw v naught y over here. Oops, let me grab all of v naught y. We'll draw it over here. Makes no difference, yeah? So you can draw it like this with v naught y like this, or you can put v naught y here, it doesn't matter. What matters is that this is an angle theta, and then just for reference I'll put it here to do the trig, but v naught x is the component along x, v naught y is the component along y, and if you're not sure how to relate it to v0 through the angle theta, well, you can always just do the following. You can just say, well, let's write cosine theta and sine theta and see what we get. Cosine theta is going to be adjacent, which is v naught x, divided by the hypotenuse, which is v0. All right. So v0x is equal to V0 cosine theta. Okay. Now, if you can look at this and get to this directly, that's great. And with practice, you will be able to do that. But if you're stuck on a problem and you're not sure, just write cosine and sine in terms of the components and then flip it around to find v naught x and v naught y. Right? Same thing with sine of theta. Sine of theta is going to be opposite v naught y over hypotenuse v naught, and then v naught y is going to be v naught sine theta. All right. Okay, so we know ax, ay, v naught x, v naught y, pretty good. And then x naught and y naught, well, those are up to you. Okay. Now, if you give me the choice, I will probably put my origin here at the launch point. Okay. Now, things can get a little tricky if you launch from a certain height. Now, maybe you want to put the origin on the ground, maybe you want to put it at the launch point. That's up to you. Okay. The placement of the origin is always up to you, unless the problem mandates that you choose a specific origin, which sometimes we do because we want to grade the same version of all the exams. We don't want everyone to pick and choose their own origin. But if I get to choose, I'm going to make it so that x naught is 0 and y naught is 0. Right? I start at the origin, so both x and y are 0 when I launch. Okay, well, with all of that, okay, with the fact that I have, there we go. I have ax equals 0, ay is equal to minus g, v naught x is v naught cosine theta, v naught y is v naught sine theta, and x naught is 0, the same as y naught. Then my equations here are very easy to derive. All right, so this is 0, and this is 0. That goes away. This is 0, and that's it. Okay? So I get 4 kinematic equations. I get x of t is equal to v naught x, which is v naught cosine theta times t, and then vx of t is equal to v0 cosine theta. And then along with that, I get equations along y, which are y of t is minus 1/2 gt squared plus v naught sine theta t, and vy of t is minus gt plus v naught sine theta. All right. Okay, so with that said, here are our kinematic equations that are going to describe the flight of the projectile. Now, there are very classic questions when it comes to projectile motion, such as finding the range, finding the max height, finding the time of flight, things like that. And these are all classic questions that we're going to tackle in the next couple of problems that we're going to do. Okay, so we could just go through and solve them in general, just for the sake of solving them, and then we could go do the problems and do the exact same thing again, or we could just do the problems. The point, however, is that you have to realize these are classic questions, right? So deriving the kinematic equations, in my opinion, should always be the first thing that you do. Even if you don't end up using all 4 of them to solve the problem, it's still nice to have them all right off the bat. And then you just have to be aware that, yes, time of flight, max height, range, things like that, speed upon impact, those are all classic questions. Okay, and so if you've practiced it a few times in practice problems and you see it again on the exam, you shouldn't be surprised. They're just extremely classic questions that show up a lot. So let's go ahead and have a look at this problem first. All right, so this is looking at Tony Parker jumping. Tony Parker, for those who don't know, is a basketball player, or was. I think he might be done, but doesn't matter. The point is, he's going to jump off the ground with a certain velocity and a certain launch angle theta. And we are reminded, of course, that we may treat him as a particle. That's because until further notice, until we get to torque and extended bodies, we will treat everything as a particle or a point mass. It's the same thing, right? So shape and size of objects don't matter. We shrink everything to a point like this, right? And we just treat it as a particle or a point mass. That means the same thing. Okay, so set up the kinematic equations for Tony Parker's motion. Okay, so once he jumps off the ground, let's find the kinematic equations. Now, hopefully we agree that whatever is drawn here is exactly what was drawn before. We launch from the ground, angle theta, initial velocity v0. Okay, so if this is x and this is y, then I should expect nothing new, right? It's going to be no acceleration along x and gravity in the minus y direction, because gravity is just gravity, right? It doesn't change. Then the components of v0 are going to be v0 cosine theta along x and v0 sine of theta along y. And we'll just choose our origin right here where we launch, so x naught and y naught are going to be 0. In other words, our kinematic equations are going to be the same as the kinematic equations we just derived. Okay, so let's just write them down so that we have them. X of t is going to be v naught cosine theta t. Vx of t is going to be v naught cosine theta. And y of t is going to be minus 1/2 g t squared plus v naught sine theta t. And then vy of t is going to be minus gt plus v naught sine theta. All right, so that's 3 points. I mean, it's even nice that you're prompted to do this. I mean, you should do it anyway, even if you're not asked to. Okay, so what maximum height does he reach, and where along the x-axis is this position located? Okay, so let's go ahead and make a copy of this thing. Let's just have it as a reference here. And of course we agree that at some point he's going to reach a max height. Looks like probably around here somewhere, right? So this is going to be, you call it h max maybe, or whatever you want to call it, doesn't really matter. And then let's say that this happens at a time t1 perhaps. I'm going to put t1 right here. And then x is going to be x1. I could call it x max, but that's confusing because it does mean, of course, x associated with the max height, but when you read x max, then you might think it's the greatest value reached along x, and that's not true, right? Because he's going to land somewhere here. So I'll just call it x1 to go with t1. Now, what I have to remember is that I have all the equations that I need. Once I have my kinematic equations to describe the flight of my projectile, whether that's a golf ball or Tony Parker or whatever, I have my equations, right? So I just need to then write what must be true at the max height and use the equations to get information about the max height and x1, okay? Now, at the max height, well, what is true? So in other words, at time t1, what mathematical equations can we write to describe the fact that we are here? All right, now there's going to be two things that are going to be true. The first one is that y at time t1 has to be h max. By definition, I'm at the max height. Okay, so that's how I'm going to get h max. If you tell me t1, I'll plug it into this, and I will compute h max. Fair enough. But I do not know what t1 is. And remember what we said last week. Very often in kinematics, you end up solving for time, even though nobody asks you to, because it's a means to an end. It then allows you to actually compute the quantity that you're after. So how would we find t1? Well, there's something else that has to be true at the max height, and that is that when you reach your max height, it's a turnaround point vertically. It means you're no longer moving up, you're not yet moving down. At that very instant, your velocity is 0. However, only along the y direction. You continue to move forward, right? By the way, you can try to cancel the velocity along x. You can't, because it's just always equal to v naught cosine theta. Because that's the initial velocity, there's no acceleration, so it never changes. Okay, so just to be clear, at the max height, you are moving forward with a velocity v naught x. However, you are not moving up, because if you were, you would not have reached your max height yet, and you are not yet moving down, because if you were, then, well, you wouldn't be at your max height anymore because you're moving down. So it's neither, and therefore Vy at t1 is equal to 0. So these two things have to be true at time t1. Okay, and we just then have to trust that from there we're going to get enough information to compute h max. Okay, so what does this look like? Well, y of t1 is equal to h max. I'll put it down here. We don't have enough room. That's going to be minus 1/2 of g t1 squared plus v naught sine theta t1 is equal to h max, and then vy of t1 is equal to 0. That's going to be minus g t1 plus v naught sine theta is equal to 0. Okay, so just to be clear, this is this, right? All I did is plug in t1 for t, and then this is this, same thing. I just plugged t1 in for t in this equation, okay? And we can do quick accounting. We have two unknowns, t1 and h max. Two unknowns, two equations, we're good to go. We don't have to write more equations, okay? But as I said last week, this is the hard part of the problem. Right, writing that is the hard part. I mean, obviously you have to be able to get this, but this is what's hard. Once you have that, once you've written things that are true, you have to trust that so long as you have as many unknowns as equations, and which means you'll have accounted for everything, then you just have to assemble things into a solution, which means you have to solve. By the way, this thing is not that hard to solve if you think about it. We would like to have t1 to compute h max. Oh well, let's just get t1 from the second equation, and then we can solve for h max. So we will start by solving. Minus gt1 plus v naught sine theta is equal to 0, and that's going to get us t1 is equal to v0 sine theta over g. And again, classic kinematics problem. Nobody asked me to find t1. I just needed to get what you want me to solve for. Okay, if you want me to find h max, I need to know what t1 is. Okay, so h max is equal to y of t1. That's equal to all of this. And now we're just going to sub t1 into this thing. Okay, so that's going to be, and it looks maybe horrendous, but it turns out it cleans up nicely. So minus 1/2 g, t1 squared is v naught squared, sine squared of theta, divided by g squared, plus v naught sine theta multiplied by V naught sine theta over G. Okay, so this is going to be, it's going to simplify a little bit, and G is going to cancel that thing. We're going to get minus V naught squared sine squared of theta over 2G plus V naught squared sine squared of theta over G. Okay, common denominator is 2G, and so we find that H max is going to be equal to V0 squared sine squared of theta over 2G, which is going to be equal to, we're at the very end now, so we can plug it in. We're going to have, well, let me write it this way. We're going to have H max is equal to V naught squared sine squared theta over 2G. That's going to be 10 squared sine squared of 50 divided by 2 times 9.8. And that's going to be pretty much 3 meters. Okay, so 3 meters is your max height. Now we still need to figure out the x location of the max height, but we found the max height. And if you think that all of this is overkill and substituting back in and then boxing your answer and everything, I am here to tell you that I strongly recommend you do this on exams. If anything, because it will set you apart from everyone else. But you should make it easy for the grader to see your work, and obviously even better if you have the literal expression first, then you plug in values, and then you get the actual numerical value for H max. Kind of is the preferred way of presenting your work, if at least if you're turning in an exam. All right. So we found H max, fair enough. Can we find x1, which is the x location where he reaches his max height? Well, remember, in kinematics, if I know time, which I do, if I know t1, I know everything. I know x, I know y, I know vy, and I know vx, because everything is a function of time. Now, of course, arguably I already used the fact that vy is 0, and I used y of t to find h max, but if I'm looking for x, well, then I'm going to use this and say at time t1, well, that's x equals x1. So the x location that we're looking for, call it x1, it's going to be x of t1, which is v naught cosine theta t1. All right, and so x1 is equal to v naught cosine theta t1. That's going to be 10 cosine, actually, you know what? Silly me. Silly me. I don't know T1. I mean, I do know T1. I don't know the value. So why am I plugging numbers yet? I need to do this. This is duh. Okay, so T1 is V0 sine theta over G, right? Okay, so this is better. Right. This is how you do it. You're going to get V0 squared sine theta cosine theta over G. And so, okay, x1 is therefore this. Okay, this is the final form where I know everything, right? I know V0, theta, and G, so I'm ready to plug in. What I was doing before made no sense. And so this is going to be 10 squared sine 50 cosine 50 divided by 9.8. And that's going to be approximately 5 meters. All right. So we found H max and we found X1. And the way we did it is by first setting up our kinematic equations, and then what we have to do is describe what had to be true at this point here. And we had to have Vy is 0, that's what defines your max height. And then once you have T1, you can solve for H max and X1. Okay. Question 3 then, find the total time of flight. All right, so let me make, again, I'm going to make a copy of this so that we have something to reference as we work on it. And we want the total time of flight. Okay, so at some point he's going to land back on the ground, of course. And let's call that maybe T final. Okay. And we have the same kinematic equations as before, of course. They're valid up until the point of impact with the ground. And we want to find T final, which means that we have to write things that are true about this location here. Okay, so what has to be true at time T final? Well, we have to have the following. So at time T final, what has to be true? Well, I can't, there's not much that I can say. First of all, I only want to solve for T final, so I need one equation. So I only need to say one thing. And the only thing I can say for sure is that y of T final has to be 0 by definition, because now I'm back at ground level. So y has to be 0. What I don't say, which is very tempting, is v final is equal to 0. Okay, that is not true. We talked about this last week. The velocity upon impact is never 0. After impact with the ground, okay, after he lands on the ground and stops, then yes, of course, velocity will be 0. That's true. But that's after the impact, okay? Upon impact, there's always velocity, otherwise there is no impact. Right? You have to be moving toward the ground to strike the ground, and as you strike it with a certain velocity. Now, after that, do you slow down to a stop because you bend your knees or something like that? Sure, that's true. But when you strike the ground, your velocity is not 0. However, y has to be 0 by definition. So that means that I need minus 1/2 of g T final squared plus v naught sine theta T final to be equal to 0. That's the same statement as y of T final is equal to 0. Now that's a quadratic, however, it's a nice quadratic because it has no constant term, which means that I can actually factor out T final and say that T final times minus 1/2 g T final plus v0 sine theta is going to be 0. And a product of terms is 0 if and only if at least one of the terms is 0. So either it's the case that T final is 0 or minus 1/2 g T final plus v naught sine theta is equal to 0. Now, of course, T final equals 0, even though mathematically it is a solution, it's irrelevant because T equals 0 is not when he lands, it's when he jumps off, right? T equals 0 is here. But it is true that T equals 0, y is 0. Mathematically, it makes sense. But you just have to toss away that option because it doesn't make any sense from the point of view of what you're trying to solve for. Okay, so then T final is going to be, now we're going to multiply by 2, divide by g. We're going to get 2v0 sine theta over g, which, by the way, if you're paying attention, is 2t1, where t1 was the time it takes to get to the max height. Okay, now that makes sense, and we're going to compute in a second, but let me say this. It makes sense from the point of view of symmetry, right? This parabola that we have here is perfectly symmetric because you start at ground level and you end at ground level. So if it takes you, I don't know, 3 seconds to make it up to T1, then it's going to take you 3 seconds to come back down, just by symmetry. However, it is not always true that T final is 2T1, right? It is purely dependent upon the fact that here we have a flat surface. We start on ground, end up on the ground, and the ground is flat. It would not be true, for instance, if you had this, right? If you were setting off to play golf at the edge of a cliff, and you were to launch your golf ball like this, and this were T1, well, you couldn't go ahead and say, well, T final is 2T1, right? That's not true, right? It's not symmetric, right? This piece is not the same as this piece. The best that you can say is this. You could say that if this is T2 here, T2 is 2T1, right? But T final is certainly not 2T1. So be careful about that, because it's really tempting to memorize T final is 2T1, but it's only true if you have the right symmetry. And in this case, the symmetry comes from the fact that we start at the ground level and we land on the ground. Like everything's flat. Anyway, with that said, T final, I'll just box this version of it. T final is 2 V0 sine theta 1 over G. That's 2 times 10 times sine of 50 divided by 9.8. And that is approximately equal to, where'd it go? 1.56, there we go. All right, so that's T final, or T flight. It's the same thing. It's the amount of time he spends in the air. Okay. All right, and then last question says, and I'm coming back up here just to make another copy of this, but the last question asks, how much time does he spend at a height greater than or equal to 3/4 of y max, or h max? It's the same thing, okay. So that's a really interesting question. Okay, so the first few questions that we solved here are super classic. Finding the max height, finding the x location, finding the time of flight. Once you have the time of flight, you could find the range. All you'd have to do is plug it into x of t. It will tell you how far he travels horizontally. But now we have to deal with a question that's a bit more specific to this problem, and that is, how much time does he spend at a height greater than or equal to 3/4 of y max? Okay, so let's just do this. This is the rest of the thing, and then let's say that this is a height. I'm not trying to draw this to scale, right? This is 3/4 of y max or h max. I guess I should have called it y max, but it doesn't matter. Okay, this is 3/4 of his max height, and we want to figure out the time spent above that portion. Right. Okay, so that's a bit more challenging, because how do I describe being above this, right, above 3/4 of h max? Now I could say, well, I'm going to solve y of t is greater than or equal to 3/4 of h max. I could, don't really want to. Whenever possible, I would prefer to not solve inequalities, because you gotta be super careful with inequalities. If you forget to switch the order because you multiplied by a negative or something, I mean, you can make your life harder than it needs to be pretty easily. Okay, so let's try to not solve inequalities. Instead, let's just say, okay, well, how about we call this, I don't know, T2, because we haven't used that yet. And maybe this is T3, right? So that at time T2 and at time T3, he's exactly at 3/4 of the max height. Okay, well, the amount of time that I'm looking for, my delta T, is just going to be T3 minus T2. That's the amount of time he's going to spend traveling above 3/4 of h max. So what I have to find are T2 and T3. So instead of solving this, I'm just going to solve y of t is equal to 3/4 of h max. All right. And so that's going to be minus 1/2 g t squared plus v naught sine theta t is equal to 3h max over 4. All right. And this is a quadratic, and it does have a constant term, and there's nothing I can do to make my life better here. I can't factor out t and solve. I just have to deal with the fact that this is a quadratic. Now, I don't like quadratics. I particularly don't like quadratics if there's fractions involved. So let's clean this up. We're going to multiply both sides by 4. That's going to give us 2g t squared minus 4 v0 sine theta t plus 3 h max is equal to 0. But quadratics are fair game, so I need to know how to solve them. I need to be comfortable saying that this quadratic has 2 roots that are going to be minus b, so 4 v0 sine theta, plus or minus, so I'll start with the minus version, the square root of b squared, which is going to be 16 v0 squared sine squared of theta, minus 4 times a times c. So 4 times 2 is 8 times 3 is 24. So minus 24 g h max divided by 2a, so that's 4g. Okay. And, well, I mean, it is what it is, right? It doesn't look very pretty, but we have everything we need to compute t1. All we have to do is plug in. And then t2 is going to be the same thing with a plus here. All right. Okay. So, but we know v0, we know theta, and we found h max anyway. So I will leave it up to you to plug in the numbers, and trust me, hopefully, and you should find 0.4 seconds for this guy and 1.17 seconds for this guy. Okay. Obviously, and I shouldn't call it T1 and T2 then. I should have called it T2 and T3. That would be a lot smarter. So T2 is going to be the smallest one of the two, right? Because you reach that point first. And then T3 is going to be 1.17 seconds. Okay. So the amount of time, so time spent above 3h max over 4 is delta t, is T3 minus T2. Okay. T3 minus T2 is 1.17 minus 0.4. That's going to be 0.77 seconds. All right. Compared to, by the way, the time of flight. Now, nobody asks me to do this. This is just me doing this to point something out. Okay, your time of flight, T final, we said, is 1.56 seconds. Right. So this pretty much is half of this. Right. So half the time he is in the air, he spends above 3/4 of his max height. And in fact, that's why basketball players appear to just float in midair when they're dunking. Okay, because half the time they spend in the air, they're above 3/4 of their max height. They're not moving very fast at that point. They're not moving up very fast, and they're not moving down very fast yet, right? But it's half of the time of flight. So it gives you the impression like that they're suspended in midair just before they come down and dunk. So interesting thing to note that half the time spent in the air is spent above 3/4 of the max height. So that is a typical projectile motion problem, right? And the approach here is going to be pretty similar in other problems. Find first set up your kinematic equations. So find ax, ay should be 0 and minus g, v naught x, v naught y, x naught x, y naught. Once you have that, you have your kinematic equations. Then expect classic questions. Max height, location of max height, time of flight, range, all of that. And then expect maybe other questions like this one here. How much time does he spend above 3/4 of h max? Well, you probably won't see that question again if you do other problems. Maybe you will, maybe you won't, but it's not that big of a classic, right? So it's more of a specific question catered to this problem. And so the idea is that the baseline is, there are a few things that you should expect to do and expect to know how to do. There are classic questions. And then from there, okay, here we have to think about it a little bit. We have to say, well, what we want is T3 minus T2. Let's try to get T3 and T2. And the price to pay was solving a quadratic. That's not necessarily always the case, but in this case it was, and so it's also a good review of the quadratic formula. Again, this is all fair game. Okay. We're going to do another problem. We're going to do another one, and the reason for it is the following. Okay, so this one's a bit more elaborate. It's not that hard, actually. It looks worse than it is, but here we're going to, before we start, we're going to point out that there's kind of three categories of projectile motion problems. The simplest is the one we just did, because if you are given v0 and theta, you can answer any question, because any answer you're going to give is purely a function of v0 and theta. That's a property of projectile motion. However, if you're not given v0 or you're not given theta, then the problem's a little harder. The first thing you want to do is find the one that's missing. Sometimes you're not given v0 or theta, neither are one of them. And the first thing you probably want to do is figure out what they are. So that's how you make these problems harder. Now, of course, if you're not given v0, let's say, which is the case in this problem, well, you're given more information about the problem so that you can back solve for v0. But nonetheless, it is the case that until you have v0 and theta, it's going to be hard to answer the classic questions about projectile motion because all the answers depend on v0 and theta, right? So the first thing you want to do is figure out what they are. So here we have a batter that hits a baseball with a certain initial velocity that is unknown, v0, at a launch angle of 45 degrees, so we do know theta. And the ball is hit at a height 1.2 meters above the ground. Okay, so that's so that we don't have y naught is equal to 0 here. So that's going to be incorporated into our equations. And we're told that the max height reached by the ball is 24.15 meters. Okay, yes, you have to give me more information if you want me to find v0, right? So that's part of it. Then we have an outfielder that is at 81 meters from the origin, and he can catch the ball up to a height of 3 meters if he jumps vertically, or he can catch the ball up to a height of 2 meters if he is standing or running at constant speed. Okay, and this constant speed at which he can run is 5 meters per second. Okay, now clearly the outfielder has nothing to do with the projectile motion part of the problem, right? You can just get rid of this right there, and you could study the path of the baseball irrespective of the presence of the outfielder. So he's probably there for later to, incorporate him into the problem. But the idea is that he can either jump, catch a ball at 3 meters above his head, or if he just stands or runs, he can reach up to 2 meters and catch a ball. Okay, and so we want to first set up the kinematic equations of the ball, and we want to figure out what the unknown is, and we want to solve for it. Okay. Let me just, before we do that, let me just say this. This is given, actually. It was, for a moment there, I thought I had forgot to erase it, but no, it's given. It's not stated in words, but it is given. He can for sure catch the ball at point B, right? Because at 2 meters, he can catch the ball at point B. Either he's got to run to it or he has to be there, but he can reach without jumping. It's just for later. If he jumps here, can he reach the ball at point A or not? So how high above his head is the ball at point A? But we'll get to that. Sorry. We're good. So let's set up the kinematic equations of the ball's motion. Let's figure out what the unknown is. We already know it's the initial velocity. Let's solve for it. Okay. Now, what is different in this problem compared to the previous problem? Well, it's not acceleration. AX is going to be 0, and AY is going to be minus G, okay, because Y is positive up. Then, well, I mean, the X component of V0 is going to be V0 cosine theta. The Y component is going to be V0 sine of theta. So that doesn't change. And here X0 will be 0. However, Y0 is H0 because the origin's on the ground. The problem chose for me, so I have to use the origin that the problem chose, and Y0 is going to be H0. Okay, so then I can set up my kinematic equations, right? I can say, well, the only difference really is X0 and Y0. It's really just Y0. And therefore, my kinematic equations are going to be x of t is V0 cosine theta t, Vx of t is V0 cosine theta, and then y of t is going to be minus 1/2 gt squared plus V0 sine theta t plus H0. Don't forget, right, you're launched from a certain height above the ground, which is H0. And then Vy is going to be minus gt plus V0 sine theta. So those are my kinematic equations. What is my unknown? Well, my unknown is V0. However, even though it's my unknown, note that it did not prevent me from writing V0 in the equations. Okay? So I just need to figure out what V0 is, and I can do that by maybe using the fact that I know Y max. Okay? But I would still use V0 in my equations. It's just that I would try to figure out how to use the extra information given to find V0, and once I have V0, I can go ahead and use these equations moving forward. All right, so V0 is unknown, and we want to solve for it. Okay, so let's briefly redraw this just real quick. Okay, now this starts at a certain height, h0 above the ground. It's going to reach a max height, y max, which is known, at a time, let's call it t1. And there are a few things that we know about y max, right, the max height. We know that Vy at time t1 is equal to 0. That's what defines the max height. Now, that's true. However, I don't know t1. But it's okay. Maybe I can write this. Okay? So at time t1, I'm going to have, so we'll say we have, the following two equations have to be true. It has to be true that y of t1 is equal to y max, and Vy of t1 is equal to 0. Right? Now this is what we just did in the previous problem. Right? I'm telling you it's a classic question, yeah? So we're going to have minus 1/2 of gt1 squared plus V0 sine theta t1 plus h0 is equal to y max. And then down here, we're going to have minus g t1 plus V0 sine theta is equal to 0. And we kind of know how this works, yeah? We're going to find T1 based on this equation, because we don't know what T1 is. And then we can plug it into here, right? And then V0 will become the only unknown of this equation, right? Completely doable. It's actually not that bad. And I'm going to do that. And I'm going to do it, well, first of all, to show you how to do it, to show you it's not that bad, but then to argue that, well, it might not be the fastest way to get the answer, but it will work, right? So when I said these 4 equations are all you need to solve, I mean it, it's true, okay? But there is a shortcut, and we'll do the shortcut in a second, right? Okay, so then this is going to give us T1 is equal to V0 sine theta over G. Now that's a good thing. I want T1 in terms of V0 because I actually want to solve for V0 so that when I plug things back into here, I keep V0 in my equation, right? So then I'm going to say, all right, so apparently minus 1/2 of G times V0 squared sine squared of theta over G squared, that's T1 squared, plus V0 sine theta times V0 sine theta over G plus H0 is equal to Y max. And it turns out I know everything but V0 in here. Okay, in fact, I even know that the first 2 terms are going to simplify, right, and leave me with V0 squared sine squared theta over 2G. We just did this before. And that's going to be equal to Y max minus H naught. Okay. And so if I want V0, I'm going to say that it's going to be 2G Y max minus H naught divided by sine squared theta. And I'll square root it, and I'll keep the positive value because, well, I just want the speed, right, and don't want the negative root. So V0 is equal to all of this, which is equal to the square root of 2 times 9.8 times 24.15 minus 1.2 divided by sine squared of 45. And that is going to be approximately 30 meters per second. All right. So we found V0, which is great because now we can answer all the other questions very easily because we know V0 and theta. Okay, but we found V0 and we did it a very classic way. We solved for time, nobody asked us to, but we needed time as a means to an end to then solve for V0. Fair enough. Okay, is there a faster way? Well, there is. Okay, remember that, and we went over this briefly last week. We said, well, you know, if you're going to go ahead and find time only to plug it back in, there's an equation that's going to take care of this for you, right? That's this third kinematic equation that does not depend on time. Right, so this is our alternate solution. We're going to say that v final y squared is equal to v naught y squared plus 2 ay delta y. Okay? Now, v naught y is known. V naught y is v0 sine theta. And well, v final y is also known. At the max height, it's 0. Okay, along x it's not, but along y, vy is 0 at max height. Okay, so then this means that 0 is equal to v0 squared sine squared of theta plus 2 times your acceleration ay is minus g, and your change in height is y max minus, now not careful, not minus 0, right? Because if you say that your change in height is y max minus 0, you mean relative to the ground. And that's not true. You started off at a height h naught, so your initial height was h naught. Okay, well you flip this around and you're going to find that v0 is equal to the square root of 2g y max minus h naught divided by sine squared of theta. There we go. So that is faster, right? But this equation has built into it exactly what we just did, right? It has built into it finding t and subbing back into y of t. And if you do that, you actually get this equation right here. So it's a nice way to solve if you actually don't care about time, which we don't. We just wanted to figure out y max. And so knowing t1 certainly is an option, but it's not a requirement to find v0 from y max. All right. So now we've found v0, we know v0 and theta, and we can answer all of the classic questions. So let me just grab a copy of this so that we can have this down here while we work. Okay. And second question is, where along x does the ball reach its maximum height, y max? Okay. Well, now that's not too bad because well, we already know, because we did the work, that t1 is v0 sine theta divided by g, right? And so the x location of the max height is going to be, let's call it x1 to match t1. Well, x1 is x of t1, just like in the previous problem. Again, super classic question, right? So it's v naught cosine theta t1, which is going to be v naught cosine theta times v naught sine theta over g. That's going to be v naught squared sine theta cosine theta divided by g. So that's going to be 30 squared sine 45 cosine of 45 divided by 9.8. And that's going to be approximately 45.92 meters. Okay. All right, that's the x location of the peak of the ball's trajectory. All right, now question 3. Come on. Question 3 asks, if the outfielder jumps vertically, can he catch the ball at point A? Okay, point A being directly above him. Right, so the ball is going to fly over him, and option A is that he jumps and he grabs the ball at point A because he can jump up to 3 meters. So if the height of the ball at point A is less than 3 meters, he doesn't have to run, he can just jump and grab it. But if it's greater than 3 meters, he's probably going to have to run to point B, because for sure at point B he can catch the ball. He can catch a ball up to 2 meters if he's running or standing still. Okay, so really the question is, what's the height of the ball at point A? Right? So let's let's say that this happens at time ta. Right. Well, what's the height of the ball? Who knows? We need to know ta. If I know ta, I know everything. Right? I know x, y, vx, vy. Okay. Now, what is true about point A? Well, there's not a lot that I know. I don't know Vx. I don't know, well, I know Vx. That's not true. Vx is always V0 cosine theta. Well, that's the problem, by the way, is that this is always V0 cosine theta, so it doesn't really help me. It's true everywhere. So Vx is not going to help. I don't know Vy. I don't know Ya. If I knew Ya, I wouldn't have to, I'd just compare it against 3 meters and I would have my answer. The only thing I know is Xa, right? Okay. All right, well, if I know Xa, then I can say that at time ta, we have Xa is equal to x of ta. All right, in other words, Xa is equal to V0 cosine theta times ta, which is going to give me ta. ta is going to be Xa over V0 cosine theta. Okay, and I know that we can compute ta, and if you feel more comfortable doing that, go ahead. I'm going to sub ta into y to get ya, but that's to practice using variables, and I want to make sure that we get as much practice as possible when it comes to solving with variables. Okay, so ta is this. Don't really care about ta. I just need it so that I can compute y of a. Okay, y of a, or y sub a, I should say, is going to be y of ta. Okay, and so that means that the height of the ball at point A is going to be given by minus 1/2 of g ta squared plus v naught sine theta ta plus h naught. And it's this ya that I'm going to compare against 3 meters. If it's more than 3 meters, he can't catch it by jumping. He's going to have to run to point B to get it. Okay? All right. Now, we've done this a couple of times already, so I'm going to go a little faster in substituting. Okay, but this is going to be minus g xa squared divided by 2 v0 squared cosine squared of theta plus, well, okay, this is v0 sine, and I'm going to divide by v0 cosine. So v0 goes away, sine over cosine is tan theta xa plus h naught. All right, so ya is going to be equal to minus 9.8 times 45.92 squared divided by 2 times 30 squared times cosine squared of 45 plus tan of 45 times xa, 45.92, plus 1.2. Is it really 45.92? Yeah, it is. Okay. And well, let's make a little bit of room for this thing. This is going to be approximately equal to, where did I put it? 10.8 meters. Okay. That's a bit high. He can definitely not catch that, right? That's way bigger than 3 meters. Okay, so ya is greater than 3 meters, so he cannot catch the ball at point A. By jumping. All right. So, ya is strictly greater than 3. He's going to have to run to point B to catch the ball. And so then we're told that if he does indeed run to point B, then how long can he wait after the ball is hit before he must start running? Okay. So, that's a good question, right? How long can he wait? Well, now he can run, by the way, at a speed v is 5 meters per second, right? Or did we, no, v1 I guess we called it, okay. So 5 meters per second. Now that means that it's going to take him 2 seconds to travel 10 meters, right? 91 minus 81 is 10 meters. He can cover 5 meters in a second, so he needs 2 meters to go from A to B. Okay, so he needs 2 seconds to run from A to B. Okay, and that's not the answer though, right? The answer is how long can he wait before he has to start running, right? What amount of time does he have to react and then start running? Well, that depends on what TB is, right? So let's solve for TB, and then we'll subtract 2 seconds, and we'll know how long he can wait. All right, so how do we find TB? Well, point B is kind of like point A. The only thing we know is x, right? So we can say that xb is equal to x of TB, right? So xb is equal to v0 cosine theta TB. All right, so then TB is equal to xb over v0 cosine theta. That is going to be 91 divided by 30 cosine of 45. That's going to be approximately equal to 4.29 seconds. Okay, so it's going to take the ball 4.29 seconds to make it to point B where it needs to be caught. Okay, so therefore he can wait delta t is equal to TB minus 2, which is 4.29 minus 2 is 2.29 seconds before he has to start running. Okay. Which, well, it's not that much time. I mean, you might have to react faster than that actually in real life in baseball, depending on how the ball is hit. But it's not that much time either to decide that you got to go run and catch the ball at point B. So again, the idea is that if you go back and you look at the problem, the classic approach is to set up your kinematic equations. We actually found that we were missing V0, so the first step was to find V0. And then from there, if you give me V0 and theta, you can ask me any question. You can ask me the classic questions, like what's the max height, or where along X does it happen? How far does the ball go, or things like that. But then you can ask me a bit more interesting questions like, given the context of this problem, can he catch the ball at point A? If he's going to have to run to B, how long can he wait before he runs? Things like that. Okay, but hopefully you see the greater picture and the trend, which is that you want your kinematic equations. Once you have them, you can answer any question. And most of the time you will see that the same questions tend to show up just because they're classic. However, that doesn't mean that you can't have a question that's specific to a certain projectile motion problem. Of course you can. So that's going to be it for the public part of this weekly review. If we look at what we did last time and this time, right? We talked about kinematics. We focused on one-dimensional kinematics last time. I'm not saying that you cannot get a one-dimensional kinematics problem on a test. You can. It's not as common as projectile motion. Projectile motion is super nice. The problems are easy to write if you're writing a test. And it tests a lot of things just in one problem. But you could still get a one-dimensional kinematics problem, certainly, right? More likely than not, it would involve either one object with 2 phases of motion. That's the rocket problem we did last week. Or it would involve maybe 2 objects moving at the same time, and each one has its own kinematic equations, right? But overall, between the last live stream and this live stream, this kind of all of kinematics that you have to be comfortable with. And I would encourage you to spend some time on kinematics. First of all, it's good to get into the habit of spending time on physics from the beginning of the course. Don't wait till midterm 1 to try to cram it all in the night before. It will be painful and not very effective in general. There's always exceptions. I have names. But in general, you want to spend some time on physics regularly so you kind of get used to it and remember, don't forget things that you learned 2 weeks ago and you can revisit them and so forth. But spend time on kinematics as well, because kinematics show up everywhere, right? You will see this is not the end of kinematics, even though we're going to move on to things that kind of look different with forces and then maybe momentum and energy and things of that nature. Kinematics have a way of always finding a spot in a problem if you really want to put them in there, right? Even in fluids, we'll see we can have projectile motion, so kinematics come back. So it's really worth spending some time on kinematics. I think if you do it now, you'll enjoy, it'll make your life easier in the long run, and you'll appreciate, rather, having done it from inception. Anyway, hopefully that makes sense and it's a bit helpful in clarifying all of this. As always, thanks for watching, because if you don't watch, this thing doesn't work. And for those of you who need more help, you can check out slackademia.com. We got some study guides and some master classes. If anything, go to slackademia.com just to enroll in the free course, which is the free Physics 8A course, or Physics 8A live stream it's called, which has all of these live streams, all of the problems, and a bunch of solved homework problems.